We're going to be looking at chemical kinetics all over again. Remember, chemical kinetics is all about how quickly a chemical reaction proceeds forwards. Now, we've got this chemical here that you've heard of before, hydrogen peroxide, H2O2. And we can see it in this little container. Now, one of the things we talk about a lot in chemistry is you never taste anything. It looks like water. It's not water. In fact, this is actually fairly concentrated. What you would get at the local pharmacy would be a 3% solution. This comes from a beautician's place, and this is a 12% solution. It's a higher concentration. A chemical reaction is proceeding right before your eyes. In fact, using Gibbs free energy, we'd say, yes, this is a spontaneous reaction, but it's really, really, really slow. In fact, for us to watch this thing actually decompose into water and oxygen would take a long time. Probably you have to wait till the cows come home. And for me, that'd be a long time because I don't have any cows. We've got this chemical reaction, this decomposition that's happening before our eyes, but we really don't see any evidence that a chemical reaction is taking place. Remember, when we think of the 5 cardinal signs of a chemical reaction, we think of the whole idea of the presence of bubbles. Now, that would certainly make a lot of sense when this chemical reaction is taking place because it's turning into hydrogen peroxide into oxygen and water. Oxygen's a gas, you see bubbles. We would be expecting that if we're seeing a chemical reaction. In addition to that, look for a color change. Well, I'm not going to expect that too much. But remember, we looked also at thermodynamics, the whole idea that heat is flowing through chemical reactions. You'll notice if you were to touch this container that it feels cool to the touch. It's room temperature. But if this chemical reaction takes place, it's actually going to release energy. That's an exothermic reaction. And so we can test it before and afterwards and see what really happens here. We also talk about the effects of a precipitate forming. Do we see something coming out of solution? Well, don't expect it to, but we'll see what happens. And the 5th one, which is something we added later on in the course, was the idea of the presence of light. So the 2 that I'm going to be interested in is looking for bubbles, and also, is there evidence of heat transformation, heat changing from one side to the other of the reactions going to the products. Keep in mind, hydrogen peroxide is actually rocket fuel. Not at this concentration, but when you start getting 90% and so, there's a lot of energy stored in this thing. So the question is, we're looking at chemical kinetics, and we're talking about 4 different factors that are going to cause a chemical reaction to speed up. We said we could increase the temperature, we could increase the concentration of the reactants, we could increase the surface area of the solid, and number 4, we could add a catalyst. Now, that's what we're going to be looking at today, looking at the addition of a catalyst to hydrogen peroxide. Now, the catalyst I have before me is actually yeast, baker's yeast. And you could do this reaction one of 2 ways. You could take the yeast just as the little spores that you have inside of the little container and put that right in here, or take this and put it in there, whatever direction you want to go. But keep in mind, if it's in a solid, the surface area is going to play a role. So what I did instead was simply take the baker's yeast and put it into solution. So now we've got a catalyst that's in kind of this aqueous solution. Here we've got this liquid hydrogen peroxide. Now keep in mind, when we're looking at catalysts, there's 2 different forms. There's one that's called a homogeneous catalyst, and that's going to be one where you're going to have the same phase of the catalyst as one of the reactants associated with the chemical reaction. The other one is a heterogeneous, and that's going to be where there are different phases. Now here, we did put it into solution, but again, it's going to be more of a solid in solution. It's more aqueous, going to have the water molecules around there. So we're going to think of it more as heterogeneous. So the question is, will this chemical reaction proceed forward quicker by the addition of this catalyst? But keep in mind, when we're looking at a catalyst, what is that? That is a substance that's going to speed up the chemical reaction by lowering the energy of activation, and it's going to be a substance that doesn't get used up. Let's take a look at the energy of activation. For us to go from the reactants to the products, we've got that hump in the middle. A catalyst is kind of like this little tunnel, this little shortcut that's going to allow now the reactants to turn into products a lot quicker. So let's go ahead and give this a whirl. And we're going to take this 12% hydrogen peroxide and we're going to add it to our yeast that's just been sitting here. And we want to see what kind of a reaction takes place. As we're looking at this, I want you to pay attention to the ferocity of the reaction. How quickly does this come up out of the container? That looks pretty quick. That's pretty fun. Also look at the size of the bubbles. Now the bubbles aren't really big. In fact, it looks like little tiny foam bubbles associated with it. But certainly, in the very process of this happening, you can say we are producing quite a bit of stuff here. We'll move this just a little bit over. Isn't that kind of fun? Look at that. Just going around and around and around. When you start using more and more of this hydrogen peroxide in terms of concentration, there's a reaction on the internet, and it is called elephant's toothpaste. And elephant's toothpaste is using 30% hydrogen peroxide, and you could use something like potassium iodide. So take a look at that. That was a pretty significant reaction. I would certainly say by simply adding a catalyst, yeast, it certainly caused this chemical reaction to get sped up, and we produce all these bubbles, which would be oxygen as well as water. Pretty cool stuff. Now the question is this kind of chemical reaction where the catalyst didn't really get used up? Well, if you look at all that, you say, well, there's probably nothing left inside of here. All that yeast probably went all over. Well, what we're going to try to do is repeat it a second time. And what's kind of interesting, just putting my hand near this, it's warm. It did give off energy. It's exothermic. So let's go ahead and take a second container. This also is hydrogen peroxide. This is 12%, and we're going to pour this in. And let's see whether or not we see this chemical reaction continuing. Notice I did not add any more yeast. All I really did was simply add more hydrogen peroxide. The yeast didn't get used up. If you start off with 1/4 teaspoon of yeast in the solution, guess what? When you're done with this reaction, assuming none of it bubbled out, you still have that same amount of yeast in there, 1/4 teaspoon. So look at that. One of the things that's really cool about all this is inside of our bodies, we have chemical reactions taking place all the time, thousands of them every second. And we have to have specialized substances that are enzymes. Enzymes are a type of protein, and they behave like catalysts. They drive chemical reactions forward. And so here we see the same idea where chemical reactions can be sped up with the use of just the right kind of enzyme, the right kind of catalyst here. So we look at that and we say, well, that was pretty cool. Certainly there must be some of that catalyst left in there because it broke down more hydrogen peroxide. So if 2 times worked kind of fun, what happens if we do it a 3rd time? Well, let's give it one more whirl. Pour it in. Let's see whether or not we're still seeing evidence that a chemical reaction is taking place. Once again, a catalyst speeds up the chemical reaction. You can see why I did go ahead and put a container here to catch anything that was an overflow, because it's kind of a fun experiment, but it can be kind of messy in the process. What can we say from just looking at this experiment by itself? Catalysts are a very effective way for increasing the rate of a chemical reaction. Let's take a look at another example. We're still going to have our 12% hydrogen peroxide. Got a few bubbles in here, and that's simply just because I poured it in there. It's not because of any chemical reaction really taking place. Instead of having our yeast as our catalyst, now we're going to have potato. Now you go, potato, what's up with that? Potato has an enzyme? Well, it turns out it actually has the same enzyme that we had with the yeast. It's called catalase. But we'll see that the concentration of this is not the same. So I'm going to go ahead and just repeat what we did before. We'll take this, pour it in, and see what happens to the hydrogen peroxide. Remember, it slowly decomposes, but the question, of course, is what's going to happen when we add a catalyst to it? Now notice we did get some bubbles, but obviously the amount of bubbles here is far, far less than what we saw associated with the yeast. Now, I would say by just simply looking at the level of bubbles that are being produced here, that this is going to have a higher energy of activation. Yes, it drops it down. The very top of it would be where there is no catalyst whatsoever with that hump. But here you can see that it's lower than actually without a catalyst, but it's higher when we compare it to yeast, where we actually had a lot of froth coming up and it's swirling around. Here's just another example where we start seeing that there's different energy diagrams. Yes, it's the same chemical reaction. Hydrogen peroxide breaks down into water and oxygen. But here we see a situation where it's not going to be as quick, but it certainly has speeded up in comparison to no catalyst whatsoever. We're going to take that same hydrogen peroxide, 12%, and we're going to add it to, believe it or not, liver juice. Well, it turns out that your liver is a protein factory, and there's all kinds of biochemical reactions that are taking place, and sometimes the product is hydrogen peroxide. And the liver has the capability of producing catalase, and catalase then helps to break down this hydrogen peroxide. Now, one thing I want you to consider as we're looking at this is how do you think this one's going to be as compared to what we saw with yeast and what we saw with the potato? Well, no better way to find out than to try it. So let's go ahead. We're going to take our hydrogen peroxide, pour it in here, and see what kind of reaction we got. And whoa, look at that. That one I would say is even more violent than what we had with the yeast. Oh my goodness, if you can see on this side, we got big old bubbles coming out of this thing. Fortunately, we've got a body that has all the right pieces, parts to respond to any kind of challenge like hydrogen peroxide that would be found in our body. It's kind of beautiful too. It's got kind of a reddish tint to it. One thing I want to mention, in veterinary medicine, we use hydrogen peroxide for a couple of things. Now, not the 12%, but the 3% like you get at the pharmacy. We use it if you have blood in your smock. You know, you're taking care of animals, sometimes they're bleeding, and you get this big blood stain right by your pocket. Well, that doesn't look very good for the next client who comes through the door with little Muffy or Fido. You got to get rid of that. And a really good way to get the actual blood out of something is pour some of that hydrogen peroxide onto that garment that's stained, and you'll see it start bubbling up, and it takes the stain out, which is kind of neat. The other thing that we use hydrogen peroxide for is if there's a concern about toxicity. The animal has gotten into something it shouldn't have, ate it, and we want to get it out of its stomach. Now, certainly certain poisons you don't get out. Okay, there's other ways you have to treat it. But if we know it's something that's okay for them to vomit it up, you actually give them a little bit of this hydrogen peroxide. It irritates the inside lining, the stomach mucosa, and it causes elevator up, kind of like a rocket ship. Kind of cool. So here we've got this example of 3 different ways we could see catalysts affecting hydrogen peroxide. Each one of these would have its own little energy diagram because we're looking at this little tunnel, this little shortcut that's going to bring the reactants over to the product side. Lots of fun. Here we've got just one dosage of this stuff, and you can still see it bubbling and burping as it's going along. It's time now to switch catalysts. Up to this point, we looked at catalase. Catalase is the enzyme that's found not only in our yeast, but also our potatoes, and we saw it with our liver. Now we're going to have one that's called manganese dioxide. And remember, energy diagrams can have various tunnels based on the different catalysts. In all situations, we should see that it speeds up the reaction, but it doesn't get used up. So let's see what happens with this one. So we're going to take our 12%, and we're going to pour it in and see what occurs. Now you'll notice they all have a certain look to them. You can see some fine bubbles in comparison when we're looking at the yeast, as well as when we looked at the one with the liver, we ended up seeing something that looked a lot more like this, where there were really, really big bubbles. And what's kind of fun is if you put your hand on the flask, which you can't do in TV land, you'd notice that this thing has definitely been heating up a little bit. But that looks kind of gassy. Look at this black stuff coming out. So this is a different catalyst, and so we'd mark this at a different position on the energy diagram. All right, one more catalyst to take a look at. We have got here our hydrogen peroxide, no shock there, but in our flask we have potassium iodide, another catalyst, another tunnel in that hump of that activation energy. And so we want to put this in here. We should see some speeding up of the chemical reaction. We should see bubbles, and if you could feel the flask, you'll feel some heat. So with not too much more said, let's go and see what happens here. You can feel the warmth, but you can certainly see that the bubbles have not gotten too crazy yet. One of the ways that we can increase this, obviously, is by mixing it. But you'll see that the reaction here is definitely not as aggressive as what we saw before, until right now. And you can see it's steaming up a little bit on the inside. It's burping a little bit there. There we go. All right, success at last. So you can definitely see there's a different character associated with each one of these catalysts for the same chemical reaction. Plus, it's always fun to see different colors. We are going to see you next time, where we're going to look at chemical equilibrium. It's not about, is the chemical reaction going to go, or how fast does it go? It's going to be about which direction does it go. Does it go mostly towards the products or towards the reactants? Thanks again for watching.